Okay, so welcome back. Uh, let's start the class. By the way, I just saw an email that this coming Friday is a holiday. You also got such an email?
Yes, it is a holiday.
It's a holiday, okay. It was announced long back or only recently?
I think it was quite some time back also.
Part of our calendar, okay. I didn't notice. Okay, so anyway, you know that. Yeah. Okay, so let's start. So what did we do last time? Last time we started this new section. So we had finished Riemann mapping theorem, and then what did we do? Yeah, we were doing holomorphic functions whose domain is the open unit disk, right? And maybe I introduced this word univalent, which just means injective, and so injective holomorphic functions. And I said that the main result that we will prove is the Kobe quarter theorem, Kobe 1/4 theorem, which we will do today. And as preparation for that, we did what is called the area theorem. So we did, meaning, I did not give all the details, but I gave you the basic idea and asked you to refer to the book. Okay, all right. So let me start sharing the screen. Please confirm that you can see. Today, and the rough history I mentioned, this was proposed by Kobe, and a few years later, Ludwig Beiberbach proved this result. Okay, and I also mentioned Beiberbach conjecture, which was proved much later. It's a modern result, 1985 or something, by Louis Debranche. So we will see, yeah. Today I won't do much. I will just do Kobe theorem. I think we have done the hard part, which is the area theorem. Not hard, but yeah, some computations were involved. So that's all that we will do today. Okay. So recall what we did last time. We introduced a certain class of functions, which we denoted by script S. So SS are all univalent holomorphic functions defined on U. So these are holomorphic functions on U, which are also injective in U. The range, the codomain can be anything. I mean, we are not restricting it at all. And we had this S had this extra condition that f of 0 is 0 and f prime 0 is 1. And therefore, the power series will look like Z plus, right? F of 0 is 0, so the constant term is not there. And f prime is 1, therefore, the coefficient of the first term, Z, coefficient of Z is 1. And so these functions have a power series expansion. And because it's holomorphic, where do you initially get the power series expansion? In a small disk, it's holomorphic at 0, around 0. So you will get it in a small disk containing 0. And because the function is given to be holomorphic throughout U, the power series expansion will be valid throughout U because U is a disk. Right. So this argument also stressed in some other context in the last class that what one is using here is if you have if you have a power series expansion and if the function is holomorphic and if you have a power series expansion, then the same power series expansion holds in the largest disk possible in the region where it's holomorphic. So here U itself is a disk. So this is valid throughout U. And we saw last time, we did this small check that if you have a function f from this set S, then there is a function g again from this set S such that g of z square is f of z square. The square of g is f square of the variable. For holomorphic non-vanishing functions. We used that and then did a little bit more check to prove this. We are going to use this today in the proof of Kobe's theorem. Okay, so given f in S, there is a g in S such that g square is f of z square. Gz square is f of z square. Then we sketched a proof of the area theorem. So area theorem, the name came because of the proof where we were computing some areas in two different ways, and you got an inequality. But what did the result say? The result states that the coefficients of a one-to-one function on U, this is not holomorphic. It is defined on U minus 0 actually, and then there's a 1 by Z term. So this has a pole. This has a pole of order 1, a simple pole at Z equal to 0, a simple pole at Z equal to 0, whose residue is also 1 wave. So it has a 1 by Z term in the Laurent series expansion plus summation alpha and Z power n. And the result says that if such a function is injective, if such a function is 1 to 1, then there is the coefficient satisfy an inequality, and the coefficient satisfy the condition summation n mod alpha n square is less than or equal to 1, where n goes from 1 to infinity. So quickly, what was the idea of the proof? First of all, because there is no alpha 0 here, you could assume that alpha 0 is 0. And then by dilating inside and outside, etc., you can also assume that alpha 1 is a real number. And then basically the idea was you compartmentalize, you divide U into 3 parts. You take an R, pick an R, and you divide U into the circle of radius R, inside the circle of radius R, and outside the circle of radius R inside U. So you consider these 3 things, and then, so if you call this function capital F, then what we proved is that so because it has a 1 by Z term, the inside the circle of radius R will be the unbounded part. So what we proved is that the annulus part, right, mod Z bigger than R and less than 1, that part is contained in a certain ellipse. And that ellipse we considered by taking real part and imaginary part of this function. Right? This you wrote as U plus IV, and then you got a certain ellipse, U square by A square plus V square by B square equal to something. Yeah. And so what you showed is that this part of this annulus part area of the ellipse and therefore you got a certain inequality for the area of the image of this annulus part. And then using the change of variables formula involving Jacobian, etc., you computed that area, a certain double integral. And here you use the fact that Jacobian of the transformation xy going to u comma v is mod f prime square, where f is this function. And these two put together, you got this inequality. So this was the idea of the proof. What we skipped was the precise computations. There was an inequality involved in the starting, which I asked you to verify, and then the precise double integral also I did not put it on below. But this was the idea. Okay. So you got this inequality, and there was a corollary which we will use today. What was the corollary? Does anyone remember? There's an obvious corollary from this.
Mod alpha 1 is less than equal to 1.
Mod alpha 1 is less than or equal to 1, right? Mod alpha 1 is less than or equal to 1. So this we are going to use today. So when I say I am using area theorem, what I am using is mod alpha 1 is less than or equal to 1 once you have such a thing. So this is all that you need to do Kobe theorem, which let's do. And that's all that I'm going to do today. So we might stop a bit early. So today we will prove the Kobe quarter theorem. So this is the theorem. Theorem is coming here in this slide. Suppose f is such a function. So what does this mean? It's a function injective on u. F of 0 is 0, f prime 0 is 1, and therefore it has a power series valid throughout u of the form z plus a2z square plus etc. So this is the power series expansion valid throughout u. And then the result is that mod A2 is less than or equal to 2. And next is the quarter part, quarter theorem. The image of the disk contains a small disk. In fact, you can say that the image contains a disk centered at 0 of radius 1 by 4. So it's a very nice result. And this is the Kobe quarter theorem proved by Babak. And I told you Babak conjecture is that this mod A2 less than or equal to 2 is more generally true. It is true that mod AN is less than or equal to n whenever you have such a function. That's by Babak conjecture, proposed in 1916 or sometime long back and proved in 1985. Okay, so let's prove this. Yeah. So firstly, you do that thing. Once you have an f in S, you have a g in S such that g of z square is f of z square. So you have such a g. And what will be the form of g? So you plug in. So these things, you have to write it down and see. There's no point of my saying it. You just have to verify. So what is f of z square? F of z square is z square plus a2 z power 4 plus a3 z power 6 plus etc. So when you take the square root of that thing, you can check. You need only the the first one or two coefficients. So you can check that it will be of the form. Just see. I mean, not form. And G is also in S. Okay. So now what you're going to do is you consider the function capital G, which is 1 by this G. So 1 by this G will be of what form? It will be 1 by this. So 1 by Z times 1 by this, which when you expand it will be 1 minus A2 by 2 Z square plus etc. So 1 by G will be 1 by Z times 1 minus A2 by 2 Z square. Other coefficients I am not bothered, whatever you get. Okay. So this is of the form 1 by Z minus A2 by 2Z and other things I am not bothered. But now remember, this is a 1-1 function. G is a 1-1 function because small g is a 1-1 function. Therefore, capital G is a 1-1 function on u minus 0. So this is like you are now in a situation like the area theorem. So if you apply the area theorem for mod G, you will get coefficients, you will get some inequality, and in particular the corollary will say that mod alpha 1 is less than or equal to 1. But what is alpha 1? Alpha 1 is minus a2 by 2. So mod a2 by 2 is less than or equal to 1. In other words, mod a2 is less than or equal to 2. So the area theorem gives you this. So take the square root of f of z square, consider its reciprocal, apply the area theorem, apply the corollary to the area theorem to that function, and that proves the first part. Mod a2 is less than or equal to 2. Okay. Now you have to prove the image contains a disk of radius 1 by 4, centered at 0. So let's prove that. So next claim is f of u contains a disk centered at 0, radius 1 by 4. So how do you do this? You show that, so if something is in this, if mod z is less than 1 by 4, you have to show that z belongs to f of u. In other words, if z is outside f of u, if z is outside f of u, you show that z does not belong here. So z belongs here, meaning mod z is less than 1 by 4. So z does not belong here, meaning mod z is bigger than or equal to mod z is bigger than or equal to 1 by 4. So if z is outside f of u, you show that mod z is bigger than or equal to 1 by 4. That's what we will do. So take something which is outside f of u. So choose w outside f of u. And you have to show that modulus of w is bigger than or equal to 1 by 4, which is what we will do. Easy proof. So consider this function h of z is f of z divided by 1 minus f of z by w. W is outside f of u. So this makes sense. No, the denominator is never 0. Why? Because if the denominator is 0, then 1 equal to fz by w, which means fz equal to w, but that is not true. W is outside the image. So denominator never vanishes, and therefore this makes sense, and therefore it's a holomorphic function. Holomorphic by holomorphic. So here you have a holomorphic function, H is holomorphic, and also H is 1-to-1 in U. How do you check H is 1-to-1? Just check. So suppose H of Z1 equal to H of Z2, you have to show that Z1 equal to Z2. Apply in the formula. So if H of Z1 equal to H of Z2, if H of Z1 equal to H of Z2, just plug it in. You will get F of Z1 by 1 minus F of Z1 by W equal to F of Z2 by 1 minus F of Z2 by W. Cross multiply, make all the cancellations, you will get F of Z1 equal to F of Z2. But if F of Z1 equal to F of Z2, then Z1 equal to Z2, because F is injective. F is in S. Script S consists of injective functions. So from the one-oneness of F, from the injectivity of F, it follows that from the injectivity of F, it follows that H is injective. So this is answered, and moreover,
I guess is that W is not 0. W can't be 0. That's why the function makes sense.
the function makes sense for two reasons. One, you are right, W cannot be 0, and the other is Fz by W is not 1. Right?
Yes.
Fz by W is not 1 comes from W is outside F of U, and we know that 0.
Of you. So
W
W
is
will
outside
contain
F.
0 because
Yeah. W is outside F of U, and F of 0 is 0, so 0 is in F of U, and W is outside F of U. So W is not 0, therefore Fz by W makes sense. And further, this is not 0. This part is not 0 because W is outside F of U. So, moreover, now let us see the power series of H of Z. Okay, so how do you get the power series of H of Z? You have the power series of F of Z, which is Z plus A2 Z square plus etc. And 1 by 1 minus Fz by W, you expand. So that will be 1 plus Fz by W plus something something. And 1 plus Fz by W, you put in Fz. And you are interested only in the first coefficient. So this is F, Z plus A2 Z square plus etc. And the next is 1 plus Fz by W, in which you have put Fz. So this will be the first part, and the rest I am not bothered. So this is the power series expansion for H, and that when you write this is Z plus something Z square plus etc. So it follows that H of 0 is 1 and H prime 0 is H of 0 is 0 and H prime 0 is 1. H is already 1, 1. H is holomorphic, so it's a univalent holomorphic function with the with this kind of power series. In other words, H belongs to S. So we have checked that this H that we have defined belongs to S. Now we are done. Now Kobe theorem follows. Because H belongs to S, what is the first part that we have proved? First part, we have already proved that once you have something in S and you have a power series expansion, the second coefficient 2 less than or equal. So this coefficient, right, this is A2, no, for this function, the second coefficient. So the second coefficient is modulus is less than or equal to 2. So 2 is bigger than or equal to the second coefficient. And second coefficient, apply the reverse triangle inequality. If you apply the reverse triangle inequality, this is bigger than or equal to modulus of mod A2 minus mod 1 by W. And in particular, this is bigger than or equal to 1 by mod W minus mod A2 from the reverse triangle inequality. And mod A2 is less than or equal to 2 also. That also you know. And therefore minus mod A2 is bigger than or equal to minus 2. And therefore this is bigger than or equal to 1 by mod W minus 2. In other words, 1 by mod W is less than or equal to 4. Right, minus 2 to this side. So 1 by mod W is less than or equal to 4. In other words, mod W is bigger than or equal to 1 by 4. So if you choose something outside F of U, you have shown that that W is outside this disk, proving this disk is contained inside F of U. So it's a very beautiful result. So very powerful result, useful result. That right? I mean, what is given to you? What is given to you is that just that it's an injective function with these properties, holomorphic, and you are saying something very concrete. You know that f of u is open because of open mapping theorem, but this says so. Open just means what? At every point, there's a small neighborhood which is completely contained inside. So open mapping theorem will tell you that D0R for some R is contained in f of u. But this is, without anything much more concrete about f, you are getting that R can be 1 by 4. And this is sharp also, you can't better 1 by 4. So let's see that you can't better 1 by 4. 1 by 4 is the best. You cannot have something bigger than 1 by 4 in general. And the example is what is called the Kobe function, what is called the rotated Kobe function. So this is given by f alpha of z equal to z by 1 minus alpha z square. Observe that these so these are functions in S. F of 0 is 0, f prime 0 is 1, and f is injective. Or you can check the power function. So power modulus of A2 is 2 alpha, and modulus of 2 alpha is 2 because mod alpha is 1. So you can't better mod A2 less than or equal to 2. Mod A2 equal to 2 can happen, as in this case. So mod A2 less than or equal to 2 is a sharp result. And similarly, in Bibabag's theorem, Bibabag's conjecture, which is proved later, mod an less than or equal to n is also sharp because the same example, mod an is equal to n. So you can't better that. In general, mod an less than or equal to n is sharp. It's a sharp result. You can't better that. Mod an is n for each n. And I haven't given assignment in some time, so take it as an assignment. Maybe officially I will ask this as an assignment only next week, because there was an email this morning that don't give any assignment for next few days. So I will. So you do this problem, you work out this problem whenever you want. I will put this as an assignment on Monday. Okay, and I will expect you to submit the answer by Tuesday or something. Okay. So the assignment asks you to do, you plot, you take one particular alpha if you want, take any alpha with mod alpha equal to 1 and then try to write generally. Okay, so question is general, but how do you attempt it? By experimenting. So the question is plot f alpha of u. U is the open unit disk. F alpha is this function. Try to visualize the image of this. And then once you write down the image, once you draw the image, you will see that this cannot contain a bigger disk centered at 0 than a bigger than D0 1 by 4. So showing that Kobe's theorem 1 by 4 is also sharp. If you take the Kobe function, then you can plot the image and you will see that you can't have a bigger disk centered at 0 bigger than a radius bigger than 1 by 4. It cannot contain. So this I leave as an assignment. Okay. So one more remark is that just introducing a word, we will soon switch topic. So Friday is a holiday, and next Wednesday when we meet, we will not be discussing these topics. We will discuss the zeros of holomorphic functions. So what I am planning to do next is the next chapter. There are many other things in this chapter, but since we have to cover a variety of things, I need to make some choices. So I will skip. If you are interested, you read the rest of the part. I will not cover it. For example, there is this very useful result when our two analysts, right? Rayman mapping theorem said that if you have any simply connected region which is not the whole of C, then it is biholomorphic to the open unit disk. So if you take an annulus, of course, it's not biholomorphic to the open unit disk. It's not simply connected. But you can take two annuli. Take one annulus, radius with radius small r1 and capital R1, and another annulus, small r2 and capital R2. You can ask when are these two biholomorphic, and you can check Rodin. There's a nice proof. It depends on the ratio of the radii should be equal. R1 by R1 should be R2 by R2. Capital R1 by small r1 should be capital R2 by small r2. So there are these kind of nice results which we should do, but I will skip because I want to go to the next topic, which is zeros of holomorphic functions. In particular, I want to do what is called the Weierstrass theorem, which I stated long back. So Weierstrass theorem would say that if you give me a set without a limit point, then I can construct a holomorphic function whose zeros are precisely the set that you have given with the correct multiplicity. I mean, if you give the set, repetitions are allowed. So I will construct a holomorphic function with zeros precisely that. So that's so that kind of topic I want to move on to. Friday is a holiday which I did not know. I just saw the email. So next Wednesday we will move to that topic. Okay. So there is what is called elementary functions, which we need to spend a little bit time. Okay. So such a function. So I'm not saying injective here. I'm not saying univalent, injective, or anything. If such a function is there, such a function has a name in complex analysis, it is called Schlicht. Schlicht function. So this is apparently a German word, and German Schlicht is German for simple or plain. So it's a simple function. It's a plain function. Okay. So Kobe rotated functions are the most famous Schlicht functions. They are also injective. That's what we used here. Okay. So I'll stop here with two. Yeah, go ahead.
In the last part, what did you say? You're not saying it's univalent.
I'm not. Oh no, sorry.
But you've written 1-to-1, right? Yeah.
Yeah, I made a mistake. Thanks. Yeah, you have been very careful. Yeah, I made a mistake. It is univalent with yeah. So yeah. So I really don't know why such a word, etc. Maybe it's historical. Right, all these people are Germans, right? Kobe and Beiberbach and also Schlist is German, is the word that they used. Yeah, so the difference with univalent is what? Univalent just means one-to-one holomorphic. Univalent does not have these conditions. This is not part of univalent. Univalent is just one-one holomorphic. And univalent function with this normalization, right? The constant term is 0 and the coefficient of the z term is 1. So that is called Schlicht. So Schlicht is univalent together with these conditions. Yeah. So this is the well-known example to keep in mind. Okay. So one more corollary and then two remarks and the class is over. We may have a short discussion session, but I need to stop a bit earlier today anyway because I have some other meeting to go to. So you take a capital F, which is holomorphic outside 0 in the punctured disk, and assume it is 1-to-1. So this is like in the area theorem. And it's exactly like in the area theorem because you're also assuming it has a pole of order 1 at z equal to 0 with residue 1. So its expansion is like 1 by z plus something, and it is 1-to-1. So it's exactly the function in the statement of the area theorem. If you have such a function, then the result says that if W1 and W2 are outside the image, so what did Kobe say? Have a univalent of greater than or equal to 1 by 4. This is not holomorphic. This is, something with 1 by z plus etc., which is 1-to-1, like in the area theorem. So corollary to Kobe is if W1 and W2 are outside the image, then mod W1 minus W2 is less than or equal to 4. So again, a very nice result. So if you take 2 points outside the image of this kind of a function, 1 by z plus something, 1 by z plus a power series, which is 1-to-1. 1-to-1 is important in all these results. Right, in area theorem, you remember, right? The proof crucially used 1-to-1. How did we use 1-to-1? Because when you considered 3 disjoint sets, you wanted to say that the images are also disjoint, non-overlapping. That was the most crucial part of the proof. So 1-to-1 is crucial. And if W1 and W2 are outside the image, then mod W1 minus W2 is less than or equal to 1 by 4. Proof is just Kobe-Quater theorem. How do we apply? You consider small f to be 1 by capital F minus one of these points, let's say W1. Right? You have 2 points outside Fu given, take one of those. So let's say W1. Then take 1 by F minus W1. Now you visualize F. F is 1 by Z plus something, etc. So when you take this F, or by cross multiplying, you can see this F will be a holomorphic function. And first of all, F minus W1 makes sense. I mean, this 1 by this makes sense because this is never 0. Why is this not 0? Because W1 is not in the image of F of U. So F of Z can never be W1 because W1 is outside the image of F of U. Therefore, because you can see the power multiplying, F belongs to S. F belongs to S. And therefore, you can apply Kobe-Quarter theorem and you will get that F of U contains D0 1 by 4. This is just the Kobe 1 by 4 theorem. Okay. And now, therefore, what can you conclude? You consider this function F minus W1 of U. This function F minus W1 of U, what can you conclude? F is the reciprocal of that and F of U contains D0 1 by 4. Therefore, 1 by F minus W1 of U contains this. Therefore, F minus W1 of U contains W such that mod W is bigger than 4 because it's a reciprocal. Right? This contains 0 radius 1 by 4 disk. So the reciprocal will contain mod W bigger than 1 by 4. This is mod Z less than 1 by 4. So this will contain mod W bigger than 1 by 4. Now use the fact that W2 is also outside F of U. And because W2 is also outside F of U, you conclude that W2 minus W1 is outside F minus W1 of U, right? W1 is constant function W1, W2 is outside F of U, therefore W2 minus W1 is outside this. So if W2 minus W1 is inside F of U minus W1, then W2 is in F of U, which is not true. So this is there and that's all that we wanted, right? So this contains this region. So if W2 minus W1 is outside this, then W2 minus W1 is outside this, and therefore mod W1 minus W2 is less than or equal to 4. Okay, so it's a corollary. Right, this contains this region. So if you take a point outside this, then its modulus will be less than or equal to 4, and this is a point outside outside this image, because both these points are outside of you. Okay, so we'll stop here with two remarks. The first remark is that this result is also the best possible, and I leave it for you to check. For example, you can take this function 1 by z plus z, and in order to check this, you can just see that both 2 and minus 2 are not in the image. But more generally, you can check that f of u is a complement of minus 2, 2, the interval minus 2, 2. So please check this, and therefore this is the best possible. Mod w1 minus w2 less than or equal to 4, you cannot decrease this 4. In general, you cannot decrease this 4. For example, that particular example, 4 does come, right? Minus 2 minus minus 2. So 4 does 2 minus minus 2. So 4 does come. In general, 4 can come. So this is the best possible. This is the first remark. And second remark is, I don't know whether you remember this result. You remember this result? When did we mention this result? I just mentioned saying that it has a proof which takes 4 or 5 pages in Rudin, and it requires many other ideas and we can't prove it. And I might have verbally stated the result. Do you remember the context when we were discussing which theorem we mentioned this?
Was it related to Osgood when we were doing that stuff? Like looking at the exercises?
It came at that time, but yeah. So what was the theorem that we did do? Osgood and all
We did
Rungest.
Rungest theorem.
theorem. Yeah. And today I was looking at the, so I must have projected just a second. Give me just a second. Yeah. So yeah, where is my screen? Yeah. So at that time I must have projected the result, and the projected result of course is correct. I must have projected Rudin's page, but verbally maybe I said it slightly wrongly. So what is Rungest theorem for a compact set? It says that if F is holomorphic in an open set containing K, then it can be approximated uniformly on K by rational functions whose poles are outside K. In fact, poles can be prescribed. That is an extra point. And I remembered Magillian as saying that instead of holomorphicity outside K on an open set containing K, holomorphic on the interior of K. This is a modern side. Holomorphicity on the interior of K. See, you need some open set to talk about holomorphicity. So interior of K is an open set, and that's enough is how I remember. But actual Magillian's theorem is only one aspect of Rungest theorem. So Rungest theorem had this corollary that if S2 minus K is connected, then rational functions can be taken as polynomials, right? Because only pole is infinity. It is that part that is generalized by Magillian. So the result, the actual result of Magillian's theorem is the actual statement is if K is a compact set such that S2 minus K is connected, and if F is holomorphic on the interior of K, then F can be uniformly approximated on K by polynomials. This is Magillian's theorem. And of course, you can ask more generally if S2 minus K is connected. Maybe there are such results, but that is after Magillian using Magillian's technique. So I don't know the correct literature. Okay, so Rudin just remarks that this corollary is used in the proof of Magillian's theorem. Of course, many other things. So I thought since we mentioned Magillian's result, I will mention that remark also. Okay, so that's all that I have for today. So we are stopping earlier than usual. It's only 10:15. But let's stop and we will have a brief discussion session, but not much time, maybe 5 minutes, 10 minutes, because I need to attend another meeting. Okay, so anyway, let me stop this recording. Stop sharing the screen and stop this recording.